Welcome to a video on section 3.1, defining the derivative. There's an argument in history that most people agree that Isaac Newton here on the left and Leibniz on the right are the fathers or the originators of calculus. One of the main topics after limits is the topic we're going to introduce today, the derivative. Now, this derivative idea comes from sort of a geometric and algebraic idea. Geometric in the sense that it's a drawing, a figure, and algebraic, and then it looks like an algebraic graph. So the secant line is where we will start. Let me show you a Desmos demo. I'm going to go over there. So, wrong screen. There we go. Notice I have the function here. It's in blue. You can see the function in blue. And then I have 2 points that I have on the graph that are kind of spaced equally apart that I can move around in the graph. If I stop this at any one point, notice the point on the left and the point on the right have the line drawn through them. That slope of that line is the average rate of change from this location to this location. And the reason it's the slope is because, remember, that's calculated as the change in y over the change in x, which will actually be the change of the function given the change in x, sometimes the change in time. So, for example, if those are about equal in height, like if we make those, there we go, about horizontal, then we would say the average rate of change is 0. In other words, from this point to this point, the function value remains the same. Let's go back to our notes. So a secant line is a straight line that intersects a curve at 2 distinct points, as you saw in the demo. Here's an example. F of x is 2x squared plus 1. I've drawn a picture on the right here, and I've picked 2 points on the graph, just kind of pick those independently. On the left, we have this point, negative 0.5 comma 1.5. So filling in the function value, f of negative 0.5 will be 1.5. And on the right, we learn that f of 1 is 3. So the secant line is drawn through those points, and then I've labeled those as such. What is the slope of the secant line? Well, we have a little background on slope. Remember that slope is the change in y over the change in x, sometimes called rise over run. And another way to find it is to just write that slope, the slope formula being y2 minus y1 over x2 minus x1. In this particular case, we have, let's take the second point to be the point on the right. So the y value is 3 minus a y value of 1.5. And then let's subtract the x value is 1 minus negative 0. That's a negative 0.5, leaving us with 1.5 over 1.5 or 1. All right, in general, given a continuous function f and some value a in the domain of f and some distance h, I'm going to label that on the graph so you can see if we start at a and go over some distance h, we can land at a plus h, as you see on the right there. We can draw a secant line through the point found at x equals a, and that's the point here on the left of the graph, and the point found at x equals a plus h, that's the point on the right. See the diagram, basically. So what is the slope of this secant line? Well, let's do the same thing. The change in y over the change in x. We're going to take the y value of the second point, that's this over here, that's f of a plus h, meaning whatever the function value is at a plus h, minus the y value of the first, which is f of a, all over the change in x, which is a plus h minus a. Quick simplification, we get f of a plus h minus f of a. In the denominator, you can see the a's cancel out, and we're just left with h. Okay, so that's what it is. Moving on. The secant line gives us the average rate of change of the function over a given interval from any place to any place. Consider a function that describes an object's position over time. If this function is linear, the average rate of change is consistent. Well, yeah, you can see from the blue line here, if we start at the left and we go to the right, no matter where we start and stop on this interval, the rate of change or the slope is going to be the same because it is a straight line. If it's a curve, we can use the secant line to find the average rate of change over a period of time. So you can see on this black function, it's kind of curving, and then it has a straight spot, and then it kind of curves again. So let's look at the average rate of change on the interval from 0 to 5 for the blue line. Well, the blue line on the left, we have 0, 0, and 5, 300 on the right. So let's do it. We could use this But remember, we have now upgraded to another formula, which I'd like to use. It's f of a plus h, that's the point on the right, minus f of a over the distance h that you went over. So let's do that. What is the function value on the right? Well, that's 300. What's the function value on the left? That's 0. What is the distance of h? Well, the h in this particular problem would be this 5, length of 5. So we have 300 divided by 5, or 60. Now, notice that this particular graph does seem to have some units. It looks like it's in miles, and it doesn't say time, so we don't know if it's miles per hour. But let me just add something here. Let's just say this is hours right here. All right, so we would have 60 miles per hour. Okay, now if you look at the black function, it turns out that the left and the right have the same values, so we would still get the 300 minus 0 over 5, or 60 miles per hour. So what part of the story is missing? Well, it's probably pretty obvious that even though they had the same average rate of change, they started at 0, 0 and ended at 5, 300, the blue went at a steady rate while the black function went at a varying rate. So we need to somehow learn to talk about what happens to the rate throughout this process to have the full story. All right, so what if we wanted to know the instantaneous, this is a new thing, instantaneous rate of change? This will be the same as the slope of a line that is tangent to the curve at a given point. So this one says imagine, because you have to do imagination. Imagine a secant line with the distance h is squeezed towards nothing. So on the right here we have a graph, I have a point, right? So what we've been doing is we have a point, and then we have another point over here, and we can draw a secant line between those for that average rate of change. Well, that's a distance of h that's pretty visible. But imagine this distance gets squeezed down to really almost nothing, so that the h is incredibly small. Maybe a point there and there. They're almost on top of each other. Well, as you squeeze that smaller and smaller, you get the idea of what we call a tangent line. Let me show you a tangent line using a different Desmos. Now here we have that same function, but notice at any one point, when I'm moving this around on the curve, it's giving me just this one point where the h is 0. And notice the line, when it seems to be going up, it's positive. When it flattens out the bottom, right, the rate of change is 0 temporarily. Here you can see it has a negative slope. And then at the top here again, it seems that the slope is temporarily 0 again. So you can kind of see the instantaneous rate of change is that instantaneous slope. Okay, great. So let's define that. The tangent line, which we will also call the derivative. This is huge. We're going to be talking about this word a lot in this class. All right. So let fx be a function defined in an open interval containing a. Then the tangent line to f of x at a is the line passing through the point a comma f of a and having the slope where this is true. What's going on here? Well, notice it's a limit. It's a limit as h goes to 0. On the top we have that f of a plus h minus f of a. That's what we had before. That's the definition of our secant. On the bottom we have the h. That's the same. But we're going to squeeze that h value down to nothing. We're basically saying the tangent line is a secant line where h is squeezed to 0, where the distance between the 2 points goes down to nothing. So we're also going to use a little bit different notation. We're going to use f prime a. We're going to pronounce that prime. It looks like a little apostrophe. That will be a way that we'll talk about our limit at a point. So let's take a look at this example here. Find the equation of the line tangent to the graph of fx equals x squared at x equals 3. Okay, so we got more than just finding this rate of change. We also want to find this equation of this line. So notice I have this green graph here. That's the x squared. And then at x equals 3, I've drawn this dashed line, which is the tangent line. So what we're going to do is we're going to find the limit as h goes to 0 of f of a plus h minus f of a. But what is our a in this particular situation? We're interested in the value of 3. So we're going to put a plus h minus f of a over h becomes, it's a little sloppy, I'll write it neater here, limit h goes to 0, f of 3 plus h minus f of 3 over h. So there we have a little upgrade. Now since we have a function, the function being x squared, we can simply just plug these values in. Let's plug 3 plus h into the function x squared. So we get the limit as h goes to 0. F of 3 plus h is 3 plus h squared. Again, we're putting 3 plus h in for our x, minus f of 3. f of 3 is just going to plug in 3. 3 squared, I know we can do that in our head, 9. We'll come back to that. Let's simplify this a little bit. Now, let's not use something called freshman's dream. We don't just square independent terms. We're going to have to square this. We're going to treat this like 3 plus h times 3 plus h. Okay, and so I guess what I'm saying here is that this is 3 plus h times 3 plus h, so you have to use the distributive property there. So if you do that properly, you get 9 plus 6h plus h squared. That's this piece, and then the 3 squared is 9, and maybe you can see what's going to happen. These 9's will cancel out, and we're left with the limit as h goes to 0 of, I'll just put the squared term first, h squared plus 6h over h. Now notice that if you put in 0, you get indeterminate, 0 over 0. But you might remember, with a limit, the factoring technique. That's what we use here. Factor out h on the top, simplifies, and then we can plug in our 0, and our limit is 6. That means this line right here has a slope of 6. We're almost done with this problem. It wants us to find the equation of the line. Okay, find the equation of the line. So since we have a slope, we also need to know this point. Remember, it's in x is 3, and 3 comma what? Well, we can just plug into the formula to know that it's at 9. 3 comma 9, because 3 squared is 9. So if we use our formula for writing the equation of a line, I like to use the point slope. Y minus y1 is m times x minus x1. Our y value is 9. That's over here. Our slope that we found with the derivative is 6, and our x value is 3. I like to clean that up a little bit. I like to write that in slope-intercept form. So you can write that as y equals, what I'm trying to say is if you distribute the 6 here, 6x, you got minus 18, but you're going to be adding a 9 to that, so minus 9. And so that would be the equation. This is an equation of this dashed line. Okay, let's take a look at another example, and then I'll have you try the next one before I try it. So this one says, find the equation of the line tangent to the graph of f of x is 1 over x at x equals 2. This time I don't have a picture, but we don't have to have the picture. We just need our derivative. So our derivative will be, we're going to look at f prime of 2, because we want to know what x is 2, is equal to the limit as h goes to 0 of f of a plus h. Now this time I'm not going to write the formula. I'll just write in my a. My a is 2 minus f of 2 over h. Okay, this time when we plug in our 2 plus h into our function, it's going to go here in the denominator for x. So we're going to get the limit as h goes to 0 of 1 over 2 plus h minus f of 2. Just put it into 2 for x, 1 over 2 all over h. Okay, this might remind you of something we did in the previous chapter where we had these complex fractions. Again, if we plug in h as 0, we're going to get 1/2 minus 1/2, 0 over 0. So that's indeterminate form. So you might remember the strategy is to just find a common denominator with the top fraction. So I'm going to multiply this fraction on the left by 2 over 2, and this one on the right by, I forgot to put my parentheses, 2 plus h over 2 plus h. All right, so let's see what we get. I'll carry it down to the next line. Fraction on the left, all of this over here, we're going to get 2 over 2 times 2 plus h minus, on the right, if we distribute the 1, there's nothing that happens there too interesting. We have 2 plus h over 2 times 2 plus h. On the bottom, we still have a h. Now that we have a common denominator, we can subtract. Notice the 2's cancel out. But the h here has a negative sign, so don't forget, we'll lose that negative sign. We'll have the wrong sign of the slope. So it becomes negative h over the common denominator, 2 times 2 plus h. All of that is being all divided by h, which is the same as multiplying by the reciprocal. I like to write it like that because it's a little easier to see that those h's will cancel out. Oh, forgot to write my limit. Let's write that in now. All right, so what do we have now? We have the limit as h goes to 0 of negative 1 over 2 times 2 plus h. Now I can see we're able to plug in the 0 because we don't have an h on top. So we get negative 1. If we plug it in the 0 for h here, 2 times 2 is 4. That is our derivative value, meaning the slope of our tangent line at x equals 2. So that is our slope. All right, so we need to use the point slope formula, just like I did on the previous one. But we don't have a point. All we have is x is 2, so we need to figure out what the y value is. And so all we're going to do is plug it into the function. So we can see that f of 2 is 1 over 2. We just put in a 2 for the x. Oh, okay, so that's your y value. So using the point slope formula, let's do that here. Y minus the y value, half, equals m, that's the slope we found from the derivative, times x minus the x value, that's 2. If you clean this up a little bit, distribute this negative 1/4, and then negative 1/4 times 2, I believe is positive 1/2. We're going to add another half, so I think we would have negative 1/4 x plus 1 if I didn't make computational error. I think I got that right. Okay, you go ahead and try the next one. Okay, I hope you've had a chance to try that one. Let's go ahead and get started. The limit as h goes to 0, by the way, what we're doing is we're trying to find f prime of 4. Let's write that in. F prime of 4 is f of 4 plus h minus f of 4 over h. And you should get the limit as h goes to 0 of square root 4 plus h minus f of 4. Square root of 4 is 2 over h. Can't plug in 0 because, again, indeterminate form. You might recognize this one as needing to multiply by the conjugate. That's the trick here. So square root 4 plus h plus 2 over square root 4 plus h plus 2. When we multiply this out, we have some good practice on this from chapter 2. So hopefully you remember all of that. It's going to be 4 plus h minus 4 on top. That's a minus. On the bottom, I'm not going to distribute. I'm just going to leave these side by side. Square root 4 plus h plus 2. Notice in the numerator, the 4's cancel out, and we're just left with h over h. I'm going to do 2 levels of simplification here. Notice this is a positive h over h would all be left on top, so those would then be able to cancel out once the 4's were gone. And then we're going to be left, I'll just write it on the next line. The limit as h goes to 0. On the top we have a 1. On the bottom we just have that square root 4 plus h plus 2. Now there isn't any indeterminate form, so you can just plug in the 0. At the top you'll have a 1. 4 plus 0 is 4. Square root of 4 is 2. 2 plus 2 is 4. That's going to be your slope. Now, we want that point. Don't forget to find the point by plugging in the value of x is 4. So f of 4, what is that? Well, it's going to be square root of 4 or 2. So our point is 4, 2. And this is our slope. So if we're going to find that equation, y minus y1 equals m times x minus x1. Cleaning this up a little bit, it's 1/4 x. Let's see, 1/4 times 4 is 1, so that's minus 1, plus 2 more, I believe is plus 1, if I did that correctly. Hope that matches. All right, let's take a look at what else we have on this. Okay, this one says you try as well, so I'm going to just give the answer at the end, not show you all of the steps. I'll show you the work, but not all the steps, so go ahead and take a moment to do that. Okay, so here is all of the work. If you need to pause the video to write it down, you can see that I evaluated f of 2 up here. I went through a lot of steps to find the limit, and I found the derivative at 2, or f prime of 2 is 8, plugged it into the formula. I have y. My final thing is, oh, I just noticed on this problem that it only did say find f prime of 2, so if you got 8, you're good. That's what it asked for. As a bonus over here, I just noticed that I didn't need to do that, but anyway, there's the equation of the tangent line if you were asked for that. But that's a little extra. It wasn't necessary in this problem. Let's take a look at derivatives at a point on a graph. So here we just have a picture. We don't have the function. It says use the graph below to evaluate each derivative. So the first one is, what is f prime of 1? What is the value of the tangent line, or the slope of the tangent line at x is 1? So that'll be about right here on the graph where x is 1. If we go up to the graph, put a point right there. If you draw a tangent line, notice the tangent line would be the same slope as the line that it's already on. So if you look at this line that's already sitting on, what is its rise over run? Well, notice from maybe from the left to the right, this looks like this starts at about 1 right here. It looks like the rise would be this height here. From 1 to 6 is about 5. And the run from here to here is from 0 to 4 or 4. So it appears that that would be a slope of 5/4. All right, and then it says what is f prime of 6? That would be going up here, drawn a tangent line. That would be the slope of this line from here to here. If if you look at the left and the right, it looks like it goes from 6 to 8. So the rise here is 2. And the run from here to here, it goes from 4 to 8 is 4. So rise over run is 2 over 4. Of course, better written as 1/2. All right, so those are the values of those derivatives just by finding the slope of the line in the graph. So here's what I want you to try yourself. Here is you can see it's a piecewise function. There's 3 separate pieces, and you're asked to find f prime of -5 and so on, these 3 on the right. Go ahead and pause the video and try those 3. Okay, so f prime of -5, you can see that that is a horizontal line. That's a slope of 0 on that line. F prime of 1.5 would be about right here. That's the slope of that second line, and we'll have to count that off. Okay, and this middle line looks like it has a rise of, oh, it's negative. So from left to right, it's going down 6 spaces. You can see from 4 to -2. This line has a slope of, goes down 6. And then it goes from -4 to 4. So if you count the spaces over, it should have a run of 8. Simplifying that fraction, -3/4. And then this last line has a positive slope. It looks like it goes up to, this one right here, and goes up to and over 5. So f prime of 7, since f prime of 7 would be a point about right there, we would have that. All right. Let's take a look at another definition. Definition: the instantaneous rate of change of a function f of x at a value a is its derivative f prime a. So that's kind of saying if we have any situation, any kind of function, and we want the instantaneous rate of change, maybe as an application, then we can use the derivative. Here's an example of that. If a rock is dropped from a height of 64 feet, let me model that. So I guess, maybe there's someone standing up on a cliff. I have no idea why. They are dropping a rock, and the rock's falling to the ground down here, and it's 64 feet from here down to the ground. All right. Its height, should be a t there, above the ground at time t seconds later is given by s of t equals, so there's this equation that gives the distance above the ground. Now that's a basic equation you would have in a physics course. The -16 is due to the gravitational pull, so there's a negative, well, when you let go of something, right, it loses elevation, it doesn't gain elevation, so it's negative pulling it earthwards. And the 64 is the starting value. So on the interval, there's an extra e, have typos on this one, from 0 to 2. Find the instantaneous velocity 1 second after it's dropped. So 1 second, maybe if it takes 2 seconds to hit the ground, after 1 second, maybe it's dropped from here to like right here, right? So it's first 1 second of flight. It's right here at this one point in time. How exactly fast is this going? So what we want, since s of t, let me just explain this out. S of t is given as the height at any time t, right? So s of t is height in feet. Then if we take the derivative of that, s prime of t, what are we going to get? Well, we're going to get the height in feet. We're going to have feet, but we're going to be, it's going to be as a rate per the variable we're looking at, per time. And maybe I shouldn't put t because we're talking about seconds, but t is seconds. So what we're going to get is we're going to get a rate feet per second. What is that? Actually, it's going to be a velocity, and later in the course we'll be using v of t a lot for velocity. So it turns out if you take the derivative of a distance function, you're going to get the velocity function for it. In this particular case, all we need to do is figure out what is s prime of 1. So going through the limit h goes to 0 of f of 1 plus h minus f of 1 over h. And so we get f of 1 plus h. Again, we're plugging 1 plus h into the function over there. We're going to get -16 1 plus h squared plus 64 minus f of 1. Maybe we can do this in our head. We'll go plug 1 into this. So 1 squared is 1 times 16. Negative 16 is -16 plus 64. I believe should be 48. 64 take away 16, I believe, is 48 over h. Okay, let's simplify this a little bit. If we have to do quite a bit of work here, but remember, when we have 1 plus h squared, you might want to do the work off to the side, like maybe just take it off to the side and do, 1 plus h squared, which is 1 plus h times 1 plus h, and do all of that distribution. You would get 1 plus 2h plus h squared. But all of that's going to be multiplied by the -16 out front. So I'm doing several steps here of algebra, but you need to take your time to work that out. So you would get -16 that's times the 1, minus 32h, that's this, minus 16h squared, that's this. And then these two last terms, 64, take away 48, I'm going to go ahead and do subtraction, which is 16, all over h. Next line. Simplify that down a little bit. Notice the negative 16 and the 16 cancel out. With what's left, we can factor out. I'm going to factor out a negative 16h just to clean this up a little bit. So the first term, I'll have 2, and the second term, I'll have h all over h. This would cancel out. And now I can plug in my 0 for h. So I have negative 16 times 2 plus 0, or negative 32. We also want to add the units since we have already thought about it over here. It's negative 32 feet per second. So what that means for us is that after 1 second of this object being dropped, it's now traveling from, started at 0 feet per second, because when we let go of it, now it's traveling at negative 32 feet per second, or in other words, downwards. The negative means downwards at 32 feet per second. So it's a really cool physics application. All right. Moving on to our last page, using a table to estimate a derivative. So a lot of times in the real world, you don't really have a function. You just have data points, and you have to use those to kind of get at what you have as the best value as instantaneous rate of change. To do so, we will average the slope of the secant lines that are found just prior and just after the point of interest. So that's where we're going to look. If we were asked to estimate at a point not listed in the data, we will simply use the slope of the line from the 2 points around it. So let's take a look at the first one. We're going to estimate f prime of 4.5. And so if you look at the table, we do have a 4.5 right here, right? But we can't just find that instantaneous rate of change because we don't know where the function is. So what we're going to do in our imagination is we're going to use the 2 points right around it, right? We're going to use this 4 and this 5 at x is 4 and 5 to look at those values. So we're going to say it's approximately, let me go back to my other pen. It's approximately equal to the slope of the secant line between those. So we got y2 minus y1 over x2 minus x1. And I might have done that a little quickly, but what I'm doing is I'm using the points from the table, right? The points 4, 7 and 5, 2. Evaluating that, we have negative 5 over 1 or negative 5. So we're going to say that the slope of the tangent line at x is 4.5 is about negative 5. That's an estimate. Next one, f prime of 5.25. Now that's not a value in the table, but if you had to imagine where it might live, it would live somewhere in here, right? 5.25 would be somewhere between 5 and 5.5. So we're just going to use those 2 points that live around it there. And so we're going to do y2. The y2 is 0 minus y1 is 2, x2 minus x1, and we get negative 2 over 0.5, which is negative 4. So those are our approximate derivative values. So let's talk about using smaller and smaller intervals to estimate a derivative. If a rock is dropped from a height of 400 feet, its height, height above the ground at time t seconds later is given by this function. Notice it's the same one as before, but we just have a plus 400 rather than a plus 64. On the interval from 0 to 5. Find the average rate of change velocity for the rock beginning at t equals 3 and lasting these many seconds. So what we're going to do is we're just going to take these smaller and smaller intervals to think about really what's going on. So let's see. If we're talking about at t equals 3, you can imagine in the table, we're not going to build a table here, but I'm thinking about when t is 3, but I'm also going to think about 0.1 second later, right? If it lasts, so it would be at 3.1. So we know at 3, all we have to do to figure out where the rock is at is just plug 3 into the function. So that's s of 3, putting that in right up here, okay? All right, for calculation like this, I'm going to pull up a little calculator. So we're going to put the the 3 in here for the t squared. We get 9 times 16, and that's going to give us 144. There's a negative on it, so we're going to make that negative 144, and we're going to add 400 to that. And that didn't give it to me, did it? So let's see, try it differently. 400 minus 144, and it's 256. All right, so this is at 256. Good, we'll have that for all of the rest of time. Now we're going to do the same thing, but we're going to plug in 3.1 into the function. So we have negative 16 times 3.1 squared plus 400. And I have 246.24. So I'll pause the video and you can do this full calculation. I'm going to write down what to do. So what we want to do is we want to find the average rate of change over those 2 points. Remember, the average rate of change would just be the slope between these 2 points. And so what you're going to do is do the y2 minus y1. There's another way to say it, but I'm saying it that way for now, over x2 minus x1. Go ahead and evaluate that yourself. All right, I have negative 97.6, and that would be feet per second. So that's the average rate of change from 3 seconds to 3.1 seconds. So it's a very, very short interval. What if we made the interval even shorter? What if we just looked from 3 to 3.01? That's 0.1 seconds later. Well, it's going to, now you know why I have the calculator. I can still borrow the 256, but I'm once again going to go through the trouble of plugging in 3.01 into the function. So let's try to get that out. So we have negative 16. We're going to multiply that by 3.01 squared, and then we're going to add 400 to that, and I have 255.0384. Okay, now we're going to take those numbers and find the average rate of change. 255.0384, subtract 256 over 3.01 minus 3. Of course, the bottom is pretty easy. That's 0.01. For the top, I'm going back to that calculator. Have that number up. I'm just going to subtract 256, and I get negative 0.9616. All right. When I divide by 0.01, I know I'm just going to move that decimal place twice. It's negative 96.16 feet per second. It's very similar, but notice as we squeeze that time down, it gets a little lower. So I want you to try the next one at 0.001 and then make just a guess based upon what you're seeing here. What would happen if you looked at the instantaneous rate of change? In other words, don't go 0.001 seconds, go 0.0000000 forever. In other words, instantaneous rate of change. So go ahead and try this last one and then make a guess, and I'll show you the answer in a bit. Okay, so I've caught up with you a bit. Maybe you've made a hypothesis, but notice that as we squeeze the time down, it was negative 97.6, negative 96.16, and now it's just negative 96.016. What if you go 0.0000001? You might imagine in your mind, oh, it's probably really close to just negative 96. And that would actually be the answer if you would go through the trouble, and you can check this after the video. I'm not going to do it here. But if you would check the limit as h goes to 0, so in other words, we're going to do that instantaneous rate of change. Go ahead and do 3 plus h, f of 3 plus h minus f of 3 over h, and just verify that that limit is actually negative 96. Okay, I hope you were able to do that, and that's all for this video.